Dr. Kurdi is an associate professor of computer science. In 2016, he moved from the University of Delaware to Lynchburg. He earned a PhD in computer science from Joseph Fourier University in France, which is a top research university, back in 2003. He's earned the Best Paper Awards at several international conferences and wrote a two-volume textbook about natural language processing, both in English and in French. He's published several papers in international journals and international peer-reviewed conferences. His specific talk today is aimed at developing a machine learning-based tool to diagnose Alzheimer's using lexical features. I'm excited to introduce Dr. Zakaria Kurdi. Thanks so much. Thank you for the presentation. So, okay, let me turn this on. So, my talk today is about developing a tool to diagnose Alzheimer, which is a disease that is very important nowadays because of the increasing number of aging people. So there are different techniques for diagnosing Alzheimer. Some of them actually use MRI, and there is a rival actually technology within AI, which is computer vision, that tries to actually detect Alzheimer within MRI images of patients. Here I'm using a less intrusive technique, which is actually using spoken language productions or written language productions of people who are suspected of having Alzheimer to tell whether they have Alzheimer or not. Okay? So the advantage of using the language as and actually of course with machine learning, the advantage is actually this method is less intrusive. We don't need to actually expose the patients to any radiation or any special, some people are claustrophobic, they don't like to be in small places, but so it's cheaper, less intrusive, has virtually no side effects, just natural speech and usually a pleasant conversation with a technician and the job is done. Now in the literature there are three big types of previous work. Of course I will spare you the details here, but the first set of work is about theoretical work which is aiming to understand Alzheimer and its impact on language. So there have been work by someone like this one actually, which is So typically those people use some picture description tasks. They give a picture to someone and they say, describe me what you're seeing. Okay. So this is important because if you have a conversation with someone, you could bias them to express themselves in a different way. So this is a more objective way to help people, express themselves. And so one of the findings of those people, among many others actually, so they confirmed the fact that lexicon is very important. Dementia has a bigger effect or impact on lexicon than, for example, syntax. Okay, syntax is viewed in linguistics as the main field, but actually here, lexicon, it seems to be more affected. And that's one of the motivations why I chose lexicon in this research. Now, another type of research is longitudinal research. So here, this lady, it seems that she's not very well known here in the United States, but she's a very bright author and philosopher in the UK. And so she published many novels, and the point is actually some people try to study her novels across the time, and it seems that one of her latest ones was a flop, a failure, partly because people think she was later diagnosed with Alzheimer. So by studying her work, those researchers were able to actually tell that that something was going on, without even having any medical symptoms actually, which is interesting. Now the third category of research is actually, which is closer to what I'm doing, is actually using machine learning and all those kind of new technologies to detect Alzheimer. So all those two categories, for example, people were just describing, using descriptive statistics. Here, we're just using machine learning to classify language productions of people saying this person does or doesn't have Alzheimer. Okay? One of the main limitations of the previous work is that people were actually using their features or descriptive characteristics of the language, sort of arbitrarily. They would say, okay, in this paper we are using this and that feature, in another paper they would use different set of features without real motivation of those features. So what I'm trying here is to be more systematic and cover as much as I could of those features. I also propose some new features to give a general overview about Lexicon and how it is impacted by dementia, and then actually do a better job at classifying that. Okay, So the aim of this work is double. First, I think, so I'm one of those old school people who think that we can solve the problem by understanding it. That might be surprising to you, but actually many of the new research right now, especially in machine learning and AI, so those people, they just try to develop a solution, and they call it black box. It works, it does the job, and nobody cares why. So here, I'm just going old school. I'm trying to understand the problem first, and then try to do the classification based on this understanding second. Okay, so that's the approach that I'm using, which is a sort of hybrid approach between a scientific work and an engineering work. So the hypothesis, given that actually many of the features that I have used in this paper haven't been used to diagnose Alzheimer, or haven't been used to at all actually, because I came up with them. So I'm assuming that, given the previous literature in general, all those features will be affected by Alzheimer. But to which degree, that's something which is one of the questions of the research. So I'm assuming all of them will be affected, but I cannot tell which one will be affected more or less, because this is one of the questions that I would like to answer in this paper. Now the data sets, that's one of the new features about this work. I've used two data sets. The first is called the address challenge data set. So the address challenge data set, that's a data set that was rearranged out of a bigger publicly available data set, which is called the Dementia Bank. The Dementia Bank is a consortium of research labs coordinated by the University of Carnegie Mellon in Pittsburgh, Pennsylvania. So those people collected different data sets from different universities, like Johns Hopkins and other top research ones. So the issue with the Dementia Bank is actually, it's not balanced, because they got resources from different places. So you may have more data for positive cases than negative cases, more data for males versus females. So here, people who actually arrange the data for the address challenge solve this problem, and the data is balanced in terms of gender, in terms of age, and in terms of condition, which is positive, negative condition. So that's the first reason why I chose the address challenge data. The second reason, actually, this address challenge data was actually compiled to organize and sort of competition, international competition between labs actually around the world, to come up with the best classifier for Alzheimer. So by using the same data set at this competition, I can align my results to those just to see whether I am within the state of the art, better, less. So that gives me the possibility of comparing my results to theirs. A second data set, so usually, say in machine learning, just to give you an idea, in machine learning what we do is, like any learning paradigm, so we train the algorithm on training data. So like we teach students on our classes, exercises and things like that. However, during the exam, typically people use different exercises to test their students. And the whole purpose of that is actually to see the generalization. That's the keyword. So did the algorithm generalize, or did it learn by heart? Obviously, learning by heart is not a form of learning, so it's nothing. So that's the reason why we have training and testing. So typically, all the machine learning algorithms will be tested on training and testing of the same data set. Okay? So here we have the address data set split in two parts, and we will be testing on the same data set, but part of it that is not being seen in the training. Okay? Now, I wanted to challenge my algorithm even further, and I collected another data set from 3 different resources, so that this new data set, the second data set, is completely different in terms of task, because here this is actually a picture description task you see a picture describing the picture, the language, etc. So here, I collected from 3 different celebrities. First of which, President Reagan, who was diagnosed with Alzheimer during his last years, and he was thought to have Alzheimer actually during the last years of his presidency, which I'm pretty sure is scary to some people here. Yes. Now, the second is actually, again, Iris Murdo. She was diagnosed with Alzheimer. And I took some, I will spare you the details, but the point with the Reagan, with Iris Murdo, and the third author, Agatha Christie, I took some of their old data, and samples of their old data, and samples of their later data, which is suspected to be during the period where they had Alzheimer. And I split those into so the old ones are negative, they didn't have Alzheimer's supposedly, and the later ones are positive, which is during the period where they supposedly have Alzheimer's. So the whole purpose of this second data set, again, is to challenge the machine learning models that will train further into sort of something that is really very different from what they have seen during the training. Now, so in this study I have covered 99 features about, I wouldn't say all, I don't know, I cannot pretend to be exhaustive, but I think all the commonly known lexical aspects. So first is lexical density that we'll talk about briefly, lexical specificity, and of course I cannot go through all those 99 features. So lexical diversity, just to give you an idea, lexical diversity is about how different are the words within a text or speech sample from each other. So if someone uses the same word all the time, that's a poor vocabulary versus someone who is creative, very sharp. So obviously, in theory, those authors should have a good diversity when they are in their health, but diversity should go down. So here are 2 other means of measuring diversity. So this is actually using something called word embedding. This is a technology that consists of converting words into vectors of numbers. Okay? This has been a huge revolution in natural language processing. And for example, ChatGPT uses word vectors like that, word embedding, as an input. Okay? One of the nice advantages of using those word embeddings is that actually you take, for example, the vector for the word lion, you take the vector for the word tiger, and you take the vector for the word Uranus, for example. In theory, if you measure the distance algebraically, cosine distance between lion and tiger, it would be smaller than the distance between lion and Uranus or planet or anything like that. So that's actually a huge progress with natural language processing that made possible things like ChatGPT, for example. Now, diversity of n-grams. So n-grams are sequences of words. So you have, if they use always the same expression, I like, I hate, or if they have diverse expressions. So that's something we can capture with n-grams. So here there's a little bit of syntax, not a lot, but a little bit of syntax. Sophistication is based on frequency. So sophisticated words are rare words. So when someone is actually using technical words that are not commonly frequent, that's actually a measurement. There are different measurements for verbs or nouns, academic word versus non-academic. So there are a lot of versions of this sophistication that I've used to detect that aspect. Now, specifically, I'll cover that. Psycholinguistic aspects are about common measurement that have been proposed by psychologists to measure the difficulty of words. For example, there is a dictionary that provides a sort of score based on the age of acquisition. So some words are learned by kids earlier, some are learned by kids later. There are different lists of also frequencies that have been developed using different criteria, so on and so forth. Miscellaneous lexical features, those are features that I couldn't put under one umbrella. So those are, for example, readability formulas. A readability formula is something that gives us a score of difficulty of a text. So, for example, in the army in the 50s, they wanted to make sure when they give the instructions to soldiers with sort of mid-school education, they don't confuse them with a language that requires college education or something like that. So I use only here the readability formulas that are based on lexicon, not out of, because I remain within the scope, not outside of the scope. And also an important thing here that I covered is sentiment analysis. Sentiment analysis, when you say positive sentiment or positive opinion versus negative one. This is a huge topic right now in natural language processing. There are so many applications that this hasn't been used to the limit of my knowledge in Alzheimer, for example. But the point is actually, there have been some work that suggested people have issues expressing their emotions with Alzheimer. So I used 3 different techniques of sentiment analysis as features just to see, and actually the results were positive in this case, but I'm just learning. So let's go to now show you 2 different simple techniques for extracting some feature. We call that feature extraction from the text. So here we have lexical density. So here we have density is the percentage of content words versus non-content words. So non-content words are, for example, prepositions, adverbs, things like that, articles. So when you have a lot of those words, but not a lot of content word, that's a poor, text or language. So usually those people don't use a lot of vocabulary within their language. However, when you have a lot of content words like movie, computer, table, so those are actually the indicative ones. So there have been debates about what to consider as a content versus non-content. For example, adverbs of time, manner, and place, they have been considered by some as content, by others as non-content, and so on and so forth. Now, let me jump to, it's just a ratio of content here. Just the point is actually with lexical density, we can just can calculate the ratio of those content words over the total number of the words, and that's basically it. We have also word frequency index and things like that. So here is actually number of lexical word or content words over the total number of words. We have the word frequency index actually here, which is we will sum the counts of the content words over the total number of words. Okay, so it's just another way of measuring this one. It's not the number here, but here we are talking about the number of occurrences. Here we're talking about the number of unique words. Okay. Now another way to measure that is actually ratios of parts of speech. Parts of speech are like adjective, nouns, verbs, adverbs, prepositions. Okay, so those are the ratios that we consider. And for every one of those, actually, I calculated the ANOVA score of every one of those features, and this is what we got. And right away, as you can see here, adverbs are the champions. So adverbs are the most distinctive part of speech, tag among all the lexical density features. Okay, why? I mean that's something that maybe requires some deep analysis. Verbs are also big. As expected, nouns also big. Adjectives are not bad, here, but here we're below the significance rate. So here, with all those other ones, actually, we are below the significance rate. Now, specificity is another type of lexical features. Now, the point here, we're talking about how precise are the words used by someone. Okay? When someone uses specific words to designate specific objects, that's a good sign of mental health, but when someone is using generic words, that's not a good sign. So just to give you an idea about a hierarchy, we have the word thing, we have the word furniture, and we have the word table. So obviously, the thing, this is called the meronym, which is the highest in the hierarchy, but meronym is not good, you need to go down. And so, furniture is better than table, but still we're high. So, so that kind of measurement of specificity, that we can use to tell whether someone is actually using specific words or designate to express himself or herself, or whether they're using generic one. So another measurement for specificity is actually abbreviations. Abbreviations are very specific, very technical words. And so when you say in French, they have CNRS. That's a very common thing, actually. This is French National Research Center. In the US, actually, what do you have as a common abbreviation like that? Yeah, so something like that. Yeah, so those are common abbreviations. If you use those, there's one single meaning. There's no other meaning to that. Now, hyponyms are the exact opposite of hypernyms. So thing is hyponym, table is a hyponym. So the lower we are in the hierarchy, the more hyponyms we have. And obviously I use an existing database for the hierarchy of the words, and so I measured that kind of things. Now this is again stats for those features. Here, ratio of the meanings of the word. So how many meanings do we have per word? That's a huge score, as you see here. It's a big winner compared to, here, that's significant actually, but still ratio of one meaning. So words with one meaning. The reason why, maybe this difference between the two is actually, there isn't a lot of one words with a single meaning. It's very technical, and within this task, maybe people don't need to use actually that kind of one meaning words. Ratio of hyponyms, how many subcategories are there within the hierarchy tree there are to a word. That's also a way to measure the generalization or the specificity. The abbreviations is null actually, because this is a spoken language task. In this case, the abbreviation is null. However, in the case of the written data, it's relevant when someone uses those kind of things. Depth of knowledge also, that's another way to measure the number of hyponyms and hypernyms. So we have 4 out of 5 significant features, among which actually, according to ANOVA, this ratio of meaning words actually is the most significant one. Now, after having done this feature extraction, what we just saw on those two figures are just ANOVA point of view, which is a possible point of view among other statistical measurements. And unfortunately, as you all know, statistics is not an exact science, so there is a way to say yes, no. So there's a gray area with statistics, so that's why I decided to go with 4 key statistical measurements. So ANOVA, of course. There's a measurement called relief F, which is commonly used for feature selection and feature ranking. So the point is, here you see the proportions of every one of those types of lexicon that we have within, according to every one of those ranking methods. So here, diversity is 46, but here, diversity for 54. As you see, the differeries aren't that huge, but still, there are some differences between the methods, and similar things can be observed with the other feature selection methods, which are chi-square and information engagement. Now, it's time to go for the machine learning experiment. So I have, now we have extracted the features. We have an idea about which features are better than others based on that. The more, if you want more details, they are in the paper, which is online. Now, for the machine learning, actually, I use 2 measures for the experiment, but I will report only the F1 because of space. So first is accuracy, which is true positive plus true negative plus true positive over n. So basically here, the correctly classified cases over the total number of cases. So it's just that. So the ones that are actually, the ones that have dementia that we classified as being AD, the ones that have no dementia that we are classified as control. We have 2 measurements actually that are used to give us the F1, that's why we need to understand. So the difference between accuracy is just a sort of optimistic way to look at the system, because we're looking at how how many good classifications did we make. Here, with the if1, which is just a measurement of a combination of the two of recall and precision. The point is we introduce false positive and false negative. So here with the F1, actually, we are looking more into the dark side of the system. That's not Star Wars or anything, but more looking at the negative side versus the more optimistic. Okay. Now I've used those machine learning algorithms, logistic regression, support vector machine, adaptive boosting, bagging, random forest, extreme gradient boosting, multilayer perceptron, and linear discriminant analysis. So those are pretty standard machine learning algorithms that I sort of used in different combinations to test different hypotheses. Now the first hypothesis is, the first question here I'm trying to answer this question. Yes, we have now different categories of lexical features. Which one does a better job than the others? So we take, for example, all the features of density and we try to test them with the machine learning algorithms. We take all the features of psycholinguistics and we try to test them with the different machine learning algorithms. So this test was done on the address challenge, and as you see here, psycholinguistics is a winner. Okay, it makes sense because psycholinguistic features are designed for this kind of purposes. So it makes sense that they are the winner, but I mean, we have miscellaneous 1 and miscellaneous 2. So miscellaneous 1 and 2, those are almost the same thing, except that here, with miscellaneous 2, I didn't use n-grams of words. Again, n-grams of words are sequences of words, 2 words, 3 words, 4 words. The reason why I separate them is actually, when you use sequences of actual words, the generalization is typically poor because it's hard to go from task to another using the same sequences of actual words. So that's why I sort of prefer to have 2 groups for almost the same thing. Okay, so actually, we got pretty decent results here with 83 for psycholinguistic features, which is not bad. Now, just for your information, the best performance reported in the address challenge is 89. Okay, so here we're 83 with psycholinguistic features alone. It's not bad. Okay, it's not bad. And also for your information, I checked minutes ago on the web. It seems that the home test of COVID, the accuracy is about 80%. So they are commercializing that. So here, I mean, it's decent. Okay, so just to give you an idea, this is not the best result, just for your information, but just to give you an idea. Now let's try to understand behind the scene what is happening. So those are called confusion matrices. Confusion matrices is just to understand how many cases of control have been classified as control for the psycholinguistic features with XG. So let's go back here. This is the psycholinguistic features. The best performance have been obtained with the XG classifier, which gave us 83. So here, we're trying to see the best performance of psycholinguistic with XG. So it actually gives us a very good performance with control and decent performance with Alzheimer. So when someone has Alzheimer, in 25%, he may be diagnosed as control. But in 75%, he will be diagnosed as Alzheimer, which is good. Now we see actually, so here it's actually more. This classifier does a better job classifying the controls than the AD. We can have classifiers that do a better job with control. For example, like this one, the density with random forest, 92% versus 8%. So the moral of this story. There is no clear pattern versus saying, okay, all the classifiers are doing a better job with classifying AD versus control or versus vice versa. There's no clear pattern. Some do a better job at this, some do a better job at that. So it's a mixed, figure here. Now, having done this first evaluation, it's time to look at the, very tough test with the generalization. So here we have the results conducted on the Murdo data set, which is, Iris Murdo, the British author. Now here, as you see, density is the clear winner. We have about 67% performance. Again, this is a very tough test. It's not an easy test. We train on something and we test on something entirely different. We train on spoken language, we test on written language. So it's a tough test. 67% with density alone, okay? The other ones actually are far behind. You see, there's a big difference between density and the other ones in the case of Murdo data set. Now, if you look at the Agatha Christie data set evaluation, things are different. Diversity does a better job, but density isn't very bad behind it, okay? And the other ones actually aren't very bad. So the figure here with Agatha Christie, the figure is more balanced in terms of, again, linguistic areas covered by this lexical study. Now the third is actually Ronald Reagan, which is here. I mean, it's more spoken language to spoken language. It's more closer. The performance is still at the, I can't see very well. So it's 68. So that's not. We're not far from 70%. It's not outstanding, but it's not too bad. Except that actually we come back to the figure that we have seen with Iris Murdo, which is interesting. So the results are pretty similar with Ronald Reagan and Iris Murdo versus Agatha Christie. Why is that? It's hard to tell actually. And here we have again, so confusion matrices. As you see here, I mean the performance obviously is poorer. In this case here, we have a big problem with Ronald Reagan and extreme gradient boosting. So with the control, in half of the cases, we actually, it's about 50-50. So we don't know what we're doing actually. However, it's better with AD. So on the other hand, so here it's actually, it's a similar pattern here, but it's even better with Iris Murdo. Opposite pattern here. So it's just again no clear picture that we can take out of that. Now, in the first experiment, I have split the features by type. Okay? Now, I will put all the features together and let the stat decide which features to be first based on their merit. Okay? We have used 4 statistical methods: ANOVA, chi-square, information gain, and relief F. So in these experiments, I take first the best feature, get the best feature according to ANOVA, get the rate. The 2 best features according to ANOVA, get the F1 rate, and so on and so forth. Okay? So this is a gradual, by the number of features. I have 99 features. So I go from 1 to 99 features and measure the performance in every one of those scenarios. Fortunately, I mean, the address data set is not gigantic. Otherwise, those kind of figures wouldn't be possible to get within a reasonable time, but that's a different story. So here, as you see, with feature selection, what we can see is actually we can improve the performance of the systems. So for example, here we have, I think it's hard to read. So we have in the 87, in this case here, we have a performance of 87. 80, I think here we have the only one with 89. So here we're touching the best performance reported by the address challenge, which is great. Now that's first observation. Second observation is more feature doesn't mean better results. Here as we see, I mean, there's a decrease in stagnation. So more features doesn't mean better results. So that's another, take out of this. So now just to recapitulate, so here among the, I took actually the group of the best features. The best features are the groups of features who help us achieve the best possible results with every one of those methods. So I took those groups and tried to actually, just to give you an idea about what I have proposed in this paper versus what I have used in this first time for Alzheimer, but haven't used for Alzheimer to the limit of my knowledge, versus features that have been used in other papers. So here, the newly used actually is 44%, old is actually 37%, and here we have about 16. So it's actually which means actually this part, which is the thing that I propose, actually plays some role among the best possible features, which is, I think, is a positive indicator. Now, another set of experiments is, again, we saw that by reducing the number of features, we could actually improve the results. Now, the question is, what is the optimal size of those text samples? Should we take longer text or should we take shorter text? So this question hasn't been addressed in the literature before, to the limit of my knowledge. So I tried to answer that question, but before that I did some basic stats in the address challenge data set. So in the training, the smallest text sample is 44. The largest is 559, and then the mean is 135. The standard deviation is 73. Okay, so we have pretty small text actually in some cases, but pretty decent ones, and pretty substantial ones in other cases. Now, what I did is actually I took gradual sizes from 1 to 225 words. Now, of course, obviously, there are cases where I have only 44 words. So if this is the case, I will take everything and nothing more. But if I have, like in this case, I have more than 225, I will take more words until I reach my upper bound. So I start with 5 words, because less than 5 words, I mean, that's absurd. I start with 5 words, and then I increment the size of the words by 1, up to 225, and try to measure the performance. Now, here, as we see, actually 2 of our feature selection methods give us a performance of about 91%, 92%, which is a small improvement, but not bad improvement, actually, to the best reported results in the address challenge. Which is, again, and then as you see here, at some point, the results, stagnate, no improvement. In some algorithms, it goes down. So, which shows actually here that we can limit the window of the words that we can take from those people, and by doing so, actually, we can improve the results. Now, in some cases here, as you see, the best performance is actually above 50. Actually, it's above 60. So the point here is the data wasn't collected in an optimal way. So for those cases where we have only 44 words in the production, those who collected, with this information here, we could have done a better job collecting the information from the patients actually, and get probably better results overall even with that. Because here again, if I have 44, I cannot do anything about it. I cannot add more. But I think that's an important aspect that can be mentioned here. Now, the other question is, does the input length limitation impact the generalization? Let's go back to our, here I just did this test with Iris Myrtle data. Now, as you see here, we have a limited performance with the 3 feature selection approaches, except for the information gain, where we have a nice peak of around 77%, which means actually with a vocabulary limitation, we could actually reach the sort of limit of 80% threshold, which is a very decent one. Now, okay, why would that be interesting? Okay, the point is, having a tool like that, putting it online somewhere, where people who suspect they have something going on, but they don't necessarily want to go and see a physician or something like that for a test, they can take this test online, and if the result is, within sort of the limit of the, if it's positive, we have pretty reasonable confidence to send those people to a physician for a further testing. I think that would be a nice way to use this kind of system, is to sort of give a first alert to people, hey, there's something going on, you should go and see someone, versus when we're confident there's nothing going on. So I think that's a good thing. Now, obviously, those are the results with the data we have. After I finished this work recently, I contacted the guy who is coordinating the dementia bank, and he told me that they just got actually a new set of data from the University of Delaware, actually, so the point is, the more data we use to train the system, in theory, the better we can get a performance, we can improve the performance. So this 78% is in theory, improvable if we get better data sets. So again, that shows that this technology is promising, I think, for a real-world application. Now, in conclusion, I have used 99 lexical features of different types. What we have seen is that all those types of features have been impacted by dementia, which is interesting. So not one of them, not some of them, and not the others. The point is actually some of them have been impacted more than the others, but all of them have been impacted. So I showed actually some of those who were more impacted more than the others, which is I think informative. The experiments on machine learning actually showed promising results. There's a small improvement of the reported results in the literature, but overall, if we think in terms of real-world application, I think the results are promising. And I think we're not far from a real-world application of technology like that. When the doctors will be obsolete, I can't tell you that, but okay, so thank you for your attention. Any questions?